Greetings to all. Today I am going to present the topic around self-organization future map, also known as KSOM. This presentation part of neural network and artificial intelligence series. Today we will discuss the concept of architecture, training, algorithm and applications of KSOM. First let us understand the concept of history of KSOM. This slide introduces the evaluation of competitive learning. KSOM is based on the concept of self-organization and competitive learning in neural network. It becomes the important technique in unsupervised machine learning. Now let us discuss the origin of self-organization. So, self-organization were developed by Dr. Kohonen in 1982. It is a special type of artificial neural network that uses unsupervised learning. The main objective is to convert high-dimensional input data into low-dimensional representation. Unlike backpropagation network, KSOM is used to competitive learning. In this method, neurons compete with each other to present input patterns. The neuron with the highest similarity become the winning neurons. Now let us understand the topology mapping. So topological mapping convert high dimensional data into one dimensional or two dimensional future map. This main goal is dimensionality reduction. The system preserves the neighborhood relationship. This means the data points that are closed into input space remaining close into output feature map. This helps us the visualization and pattern recognition. Now let us see the architecture of KSOM. This slide explains the architecture of KSOM. The input layer contains raw data features. The unknown layer consists of neurons arranged into two-dimensional lattice where competition occurs. Weight occurs there are adjustable connections that store organized future information. In this architecture, each neurons corresponded to specific input feature and learning pattern during training. Next, now let us understanding the winning and unit selection process. In KSOM, competitions occur before learning. The neuron with the highest similarity to input vector becomes the best matching unit or winning neuron. The input vector is compared with all neurons using weight matrix. The winning neurons and neighboring neurons update their weights. This helps to the organization similar pattern together. Now let us discuss the training algorithm. The training algorithm includes initiation, distance calculations, winner selections, and weight updating. Now let us see the training execution phases. Here, step 0 begins the random insertions of weight and setting the learning rate. Step 1 and step 2 involve the interactions through each input vector until stop conditions is reached. Step 3 calculates the Euclidean distance for all neurons. Step 4 identify the winning neurons with minimum distance. The neuron is continuously completed and adjusted during time. Now let us look at the distance calculation formula. This slide shows Euclidean distance calculation formula. The distance between the input vector and each neuron weight vector is calculated. The neuron within minimum distance become the winning neurons. This process helps identify the best matching unit. Now let us see the weight update law. So this formula is used to update the neuron weight during learning. The new weight is calculated using old weight, the learning rate and input vector. The winning neurons and neighboring neurons update their weight together. Alpha represent the learning rate which control how much adjustment occurs. Now let us understand the conversation dynamic. During training, both learning rate and neighboring radius decreased over time. In this graph, we can see alpha and radius gradually reducing as a epoch increase. This helped the network stabilize and improve accuracy. The formula rate update equations controls gradually converge, con- convergence. Now let us see the real world applications of KSO. Head-on self-organization mapping is widely used in real-world applications. The data clustering. The organization unstable data sets into meaningful clusters. Visualizations. The converted complex high-dimensional data into easy to understanding 2D maps. Anomaly detection. The anomaly and they identify unusual data points or outer line. The The cluster visualization map help, helps easily inspect grounded patterns. Finally, let us conclude the presentation. So this brings us to end of the presentation on KSOM. Thank you for listening. Now I am